Hello and welcome to this first in a short series of videos on the subject of noise in electronic circuits. In this series of videos we'll be looking at what noise is, where it comes from, how to identify different types of noise, how to calculate the levels of noise that we would expect to see in circuits, and a quick look at some techniques to minimize noise in circuits. In this first video, we'll be looking at what noise is and how it is characterized in terms of its power and its amplitude. Noise can occur at any frequency, but it's often associated with audio frequencies. And audio noise sounds like this. That's a particular type of noise called Gaussian white noise. We'll come on to why it's called Gaussian and white noise in future videos. But for now, just note that that is one of the most common types of noise that we have to deal with in electronic systems. Perhaps the most important feature of noise is the fact that it's unpredictable. If it were predictable, of course, we could generate an equal and opposite signal to the noise and cancel it out, and it wouldn't be a problem. It's that very unpredictableness, that random nature of noise, that makes it such an issue in electronic circuits. It is, for example, impossible to write an equation that will predict the noise at some time in the future. However, what we can do is characterize the noise in terms of its probability distribution. How likely it is that the noise will take any particular value at any time in the future. And doing that allows us to produce an expression for the average or mean power in any noise signal. The power in any noise signal is calculated in exactly the same way as we would calculate the mean power in any other signal. You take the signal, square it, take the average value of that, and that gives you the mean power. In other words, the power is the square of the RMS amplitude. And we tend to talk about noise in terms of its power rather than its amplitude, because for a lot of noise in electronic circuits, the amplitude is, at least in theory, infinite. This means that if we were to double the noise power, the noise amplitude wouldn't change. It would still be infinite. And just quoting the noise amplitude as, in theory, infinite, doesn't tell you anything about the noise power. Because in order to work out the average noise power, you would need to know how likely it was that the noise voltage took any particular value. If the noise voltage did occasionally shoot up to huge levels like kilovolts, that would only have a significant effect on the noise power if it went up to those huge levels reasonably often. In fact, the type of noise that we deal with in electronic systems is incredibly unlikely to take these very large values of noise. So those huge values don't have a significant effect on the noise power. Also, in many cases, it's the average noise power that is important from a systems point of view in determining how much the performance of the system degrades. So we'll be talking a lot about noise powers. We will be talking about noise amplitudes as well, but it's often easier to bear in mind that when you're dealing with noise, it's better to deal with noise powers rather than noise amplitudes. And when we do talk about noise amplitudes, it's usually better to think about those as the square root of the noise power. That's all for this first one. In the next video, we're going to look at probability distributions in a little bit more detail and see how you can use them to calculate the mean value in any noise signal given knowledge of their probability distributions.